Hello. Hello? Okay, cool. Hello. Okay, let's get started. So, do we have any question from this time? Anyone? If okay, then yeah, let's get a quick review of this time and then trying to make it a bit faster for the two chapters. So, I push to finish chapter 1 today, but we'll see what happens. Okay. Anyway, so quickly review from this time, we start to talking about this discrete and complex exponential. And it looks a lot like a continuous and complex exponential. It looks like e to the j omega naught n. It's just changing e to the j omega t to e to the j omega n. But then we see that when we consider the periodicity of this discrete and complex exponential, it's very different from continuous time case. So first is that when you increase the omega, when you increase this omega 0, it doesn't the frequency doesn't necessarily increase for your function. Indeed, when you increase omega 0 by 2 pi, your function doesn't change at all. So the frequency, the signal is kind of periodic in the frequency. Meaning that the frequency only has meaning in 0 to in 2 pi length 2 pi region. Okay? And another thing is that the period is not just 2 pi divided by omega 0 anymore. Okay? Because we find out we know that the period needs to be a positive integer. Okay? And that means that the period is going to be 2 pi divided by omega 0 times some integer m. Okay? So the fundamental period will be the smallest number that satisfies this thing. And so we have some example here. So I guess my personally a way to look at this is you think about what's omega 0 divided by 2 pi. And if it's a rational number, it can be written as m divided by n. And so, for example, if your omega 0 is 2 over 3 times 2 pi, then you know that your big N is this 3, and then you have this n being 2, means that in the period of this 3 distance, your signal goes phase by 2 times 2 pi. Your signal like oscillating twice. Okay. And anyway, so we have some pictures showing that how the discrete time finite sampling affect the behavior of the complex exponential signals. And here we actually plot sinusoidal, so that's the real part of the complex exponential. And we see that in continuous time, when you keep increasing this omega 0, your signal just oscillating faster and faster. But for discrete time, your signal oscillating fattest when your omega 0 is pi. So here we are written in terms of 1 over 8 times something times pi. So we see that the fattest oscillation can get is when omega 0 to pi. That means your signal just go from 1 minus 1, 1 minus 1, 1 minus 1 at each time step. And when you increase the frequency even higher, your signal actually goes back to looking like your previous signal. So the omega 0 equal to 1 over 8, omega 0 equal to 15 over 8 pi. And finally, when your omega 0 is just 2 pi, then you get back to a constant function. And you're increasing, then you start oscillating again. Okay. And then let's go back to the part that we said we'll do today. That's, I guess this is a review. Any question? If not, then then let's start to have more example calculating the period for discrete time complex exponential sinusoidal. Okay, and so first we have the example here. So we've x of t equal to cosine 2 pi t divided by 12. Then you can have the period is this 2 pi divided by this 2 pi divided by 12. So t is 12. And and then you plot this as x of n, then you have cosine 2 pi divided by 12. Then your big N is also 12. So it's easy. It's just where you go to 12 plus go to distance 12. Then it goes is up and down, and you go to 1 period. Okay, and so this n is 12. And then, well, we have a more tricky example. So x of t equal to 2 pi times 4 over 31. And for continuous time case, you can just calculate the fundamental period as 31 over 4. And now for discrete time case, you have cosine 4 over 31 times 2 pi. So your omega 0 is 4 over 31, and then you think your period is 31 over 4. So 31 over 4 will be kind of like one of these oscillations here. And so I guess it's really we can do a bit of testing here. So do people think this is correct for n equal to 31 over 4? If you think this is true, raise your hand. If you think this is not true, then raise your hand. Okay. And similarly we have this question. So when x of t equal to I guess we can do some testing here. So for those of you who think n is not 31 over 4, what do you think n is? Anyone want to answer? What is the fundamental period here? Okay, please. Yeah, yeah, indeed. So there's a bigger number here. The 31 will be the n, and what happened is we're oscillating 4 times, and you will get back to the correct phase, and so that will be 31 here. Okay, and the distance here will be 31 for 4 oscillations. Okay, and what about the next example? Now the omega 0 is 1 over 6. And is n equal to 12 pi. For those of you who think n is 12 pi, raise your hand. And for those of you who think n is not 12 pi, raise your hand. And once again, if n is not 12 pi, what is the fundamental period here? You want to answer? You should.
It's not periodic.
Yeah, that's correct. This is not periodic. Okay, and indeed, so as we said before. As it is, as he answered. So when omega 0 is 2 pi times 31 over 4, we have begun at 31. And if omega 0 is not a rational multiple of 2 pi, then this is not periodic, because you keep increasing this thing. Although it looks like periodic, every time you go to this intersection here, you will have a different phase inside, just because this is not a rational number inside. Okay? No, sorry, not a rational multiple of 2 pi inside. Okay? And so indeed that's all we want to talk about. So to find the fundamental period of discrete time complex exponential, then you look at omega 0, you write it as 2 pi times n over n, and then you find small is m and n here, and so this n will be your fundamental period, and m will be your fundamental frequency. Okay, and I guess this is a little sorry, n will not necessarily be fundamental frequency. So if it's a negative number, then it's a bit more tricky. So if negative number, then fundamental frequency will be 2 pi divided by n, and that will be actually be absolute value of m. Okay, and yeah, so that's for periodic signal. And if it's not a rational number times 2 pi, then the signal is just not periodic. And we have a table here for more review information. Okay, so let's skip this and let's go to the next example. I guess this example we can do pretty fast. And so now we have a linear combination of two complex exponential, and we can find the fundamental period of each one of them. Okay, and so the first one of them, e to the j 2 pi divided by 3n. The omega 0 here is 2 pi divided by 3, so this n over n is 1 over 3, so we just know big N is 3 here. And the second one is e to the j 3 pi over 4, and 3 pi over 4 is 2 pi times 3 over 8, and so we find big N equal to 8 here. And now we want to find the fundamental period of both of these signals, so this should be something that's a multiple of this period and a multiple of this period. So you just find the least common multiplier of 3 and 8, and you find out the fundamental period here is 24. And yeah, we have a few more slides with more detailed explanation of this, but the idea is basically this. We'll talk about you can do a smaller search, so you can keep increasing your period, and to find the fundamental period, yeah, etc. Okay, and so that's this example, and then I guess this is the last topic about discrete and complex exponential. Is just like continuous time. We want to talk about harmonically related discrete time, discrete and periodic exponential. Okay, so what are those harmonically related complex exponential? They are complex exponentials that all share a common period. So let's say the common period is big N here, and here we skip the derivation, and because it's very similar to continuous case, and you find out whenever your signal has this form, phi k of n equal to e to the jk 2 pi divided by n 2 pi divided by big N times small n, then this is periodic in period with period big N. Okay, that's this is you can kind of verify this from previous example, because if I want to write down the omega 0 for this thing, will be k divided by big N. Okay, so n is not necessarily the fundamental period of this thing, but it will be a period of this thing. Or you can check it straightforwardly. I guess if you just think what happens when n go to small n go to from small n to small n plus big N. Oh, here we are checking. Sorry, this is a different thing. So you can check when small n go to small n from small n to small n plus big N, then you get h. So the big N will cancel this big N here, so you get the extra 2 pi k phase here. So that doesn't change your signal. Okay, so this is periodic with period N. And now the difference between this thing and the continuous case is that continuous case you can have infinite number of different k, and there will be all different signal. But in discrete case, once again your frequency cannot go too high, so your k that translates to your k cannot go too high. So there are actually only n different k's that give you different signal here. And that's expressed in this relation, where you see that when you change your k to k plus big N, so basically you increase your frequency by 2 pi here, and as we know, if you increase the frequency by 2 pi for discrete signal, I guess I say frequency is a little weird, but by frequency we mean the omega 0 term here. Okay, so you increase the k to k plus big N, so increase 2 pi on this exponent here, then the signal doesn't change. It's still the same signal. Okay, and so there are only big and different harmonically related discrete complex complex exponential signal, and you can, so basically you write n consecutive different big small k here, and there are different choices here, but so the simplest choice is you have k from 0 to n minus 1. but sometimes you also, so just like when we talk about frequency, sometimes we go from 0 to 2 pi, sometimes we go from minus pi to pi. And yeah, so for this k, sometimes we will also write this k equal to bigger minus 1 as k equal to minus 1, and as k equal to minus 2, minus 3, etc. Okay, but you just need to pick some interval of k. Okay, and then we can reuse our picture before and to see what harmonic related signal look like. Okay, and so those signals are all signals with bigger n equal to 16. Okay, and we see that when k equal to 0, you have a constant signal, and when k equal to 1, then you see your signal oscillating once in those 16. in this period of 16, and when k equal to 2, your signal oscillates twice in this period of 16, and when k equal to 4, you are oscillating 4 times, but this is pretty pretty extreme already. And finally, in k equal to 8, this is a special k because it's half of n. Okay, when your k equal to half of n, then you see your signal should be e to a j pi n, and we know e to a j pi n is the highest frequency you can have in complex exponential. Okay, so k equal to n over 2, k equal to 8, then you have this highest frequency here, and then once again in in the period of 16, your signal kind of oscillating 8 times. Okay, and when k equal to 12, then your signal kind of go back. Okay, I guess we talked a bit wrong before. Okay, so k equal to 12, then then you see your signal actually look a lot like k equal to 4. And I believe those two are actually the same because you are only looking at the real part of the complex exponential. Okay, and anyway, so k equal to 12, it looks a lot like k equal to 4, and k equal to 14, it looks a lot like k equal to 2, and k equal to 15, then k equal to 15, then it looks like k equal to 1. Although if you write a full complex exponential, then I think the sign part you will get a negative sign. Okay, and yeah, finally k equal to 16, you go back to same as k equal to 0. Okay, and anyway, so this is k equal to 0 to k equal to 15 are the 15 different harmonic related complex exponential. Although we are writing down only the cosine, with only a real part, so some of them actually look the same. So this k equal to 1 and k equal to 15 look the same. But you write down the I sine theta part, they will be different. And but back to our periodicity in k, and when k equal to 17, you see it's actually same as k equal to 1, and k equal to 18, same as k equal to 2, etc. K equal to 20 equal to k equal to 5. Okay, so that's the end of our discussion on discrete time complex exponential and its periodicity. And any questions so far? If not, then then we'll go to a totally different topic. Those we have 2 or 4 signals that are going to be very useful in next chapter, and we'll give you a brief introduction here. So there are the unipulse function. This is delta of n or delta of t, and the unit step function u of n and u of t. They are very useful because, as we'll see in next chapter, we can decompose any function into linear combination of delta of n and u of n. Okay, and anyway, let's go to see what those signals look like. So first is the delta of n. This is easier. It's a very simple signal. It's a signal where it's a 0 everywhere and 1 and n equal to 0. Okay, so it just look like this. And the nice thing about this is you can shift this thing around. So remember we do time shift on signal before. So if you want this spike here, so this this height of 1 spike here. If you want to move it other place, you just change it from delta of n to delta of n minus n0. Then you see that this delta of n minus n0 is a function where it's a 0 everywhere, except that n0 equals to 1. Okay, so it's a very simple function, and yeah, it's nice before it's being simple. Okay, and then we have a bit less useful function, but it's still nice to know its name. So it's a unit step function u of n, and it just looks like this. So it's a 0 everywhere, 0 for n less than 0, and 1 when n greater or equal to 1. Okay. Oh, sorry, n 1 when n greater or equal to 0. So when n equal to 0 is still 1. Okay, and once again you can move this. So it look like step because it was 0, and it look like a step in a staircase. So you move one step up to this function value all being equal to 1. And you can also move the location of this step by just doing a time shift on your variable n here. So you have n minus n0, this step will located at n0. Okay, and something to memorize here. So you should remember the name unit impulse, unit step, and this delta notation. So delta of n will just will reserve this delta symbol here for unit impulse. Whenever you see delta of n, it means this function, and also we'll reserve this u of n symbol here. U of n means this unit step function. Okay. So just the notation to remember here: unit impulse equal to delta of n, unit step equal to u of n, and I have those very simple form. Okay. And there are some relationship between unit impulse and the unit step, and I don't want to go to too much detail because we don't actually use too much of them, but it's nice to know. So basically, you can there is a strong relationship between delta and u. So you can get delta from difference of u. So you can just think about you have a u of n minus u of n minus 1. Then this is a step start from 0, this step from 1. So you subtract this function from this function back to this delta function. Okay, and then you reverse this difference to summation. Then you can get u of n as summation of delta of n. And that's omit some detail, but you can change some variable, you can do some change of variable, and so different kinds of ways of summation of delta of n or go back to this u of n. Okay, and yeah, so let's skip this part. But I guess one of the nice way to see this summation is that if you can get u of n from this kind of summation. This is nice because we will go to see similar thing in continuous sum case. Okay, so you just place the delta of n here. Actually, it's delta of m. Okay, so you need to be careful about change of variable here because you want to sum something, so you have another dummy variable m. Okay, so you write the delta of m here, and you think about you summing over some range from minus n to minus infinity to some number. Okay. And so the number will be n, so this n is this n here. And so you think about this summation, and if this summation doesn't include this spike, then obviously you are summing over a whole bunch of 0, you get 0. And if the summation range includes this spike, that means when n is greater or equal to 0, then you will get 1. Okay. And then this function is exactly u of n. Okay. So this is a nice property to know. Okay. And yeah, then there you can do some change of variable to get u of n as a different summation. So this is summation of delta of n minus k. Okay, and but let's skip the detail here. And now let's talk about a property very useful for us is the sampling property. Okay, and so why we like delta of n a lot is because you can help us figure out the value of some function at some specific point. So for example, if you multiply any function or any signal x of n with delta of n, then you see that because delta of n is 0 everywhere, then this thing only depends on x of 0. And and the effect when n equal to 0, this is just delta of n was 1, so this is just x of 0 times delta of n. Okay. And so you find out that you multiply x of n with delta of n, then this is pick out a sample of your x of n. You just sample your x of n at n equals 0. So x of n times delta of n become x of 0 times delta of n. Okay. Yeah, so I guess I could say x over 0 here, but yeah. So x of n times delta of n look like this, and this function is x of 0 times delta of n. Okay, and so this is picking out x of n at n equals 0. And if you want to pick out different value, then you just change your delta of n to delta of n minus n0. So say your n0 was 5, so you multiply your x of n with delta of n minus 5, then your function become delta of n minus 5 times x of 5. So you will see get the x of 5 here. Okay, so this is a very important sampling property of the unit impulse function. Okay, any question? I think the discrete Han unit impulse function and the unit step function are pretty straightforward. There are those two functions, and you multiply a function with the unit impulse, you can sample it at different points. Okay, and now things get weird, a bit weird when you think about continuous design case. So in continuous design case, you also want a function that sample your continuous time signal at a different point. Okay, and so we'll define this unit step function. Unit step function is relatively straightforward. So it becomes still this step function, but just become continuous time. So it's 0 when t less than 0, and 1 when t bigger than 1. Okay, and but we already see some singularity here. So when t equals 0, we actually say this is undefined. So there are different conventions here. Some people like to have u of 0 equal to 1 half. Some of them like equal to 1. Some of them like equal to 0. But for this course, we just say it's undefined to keep things a bit simple. So u of 0 undefined. Okay, and then we have a unit impulse function, and it's a really weird function. So if you are mathematical rigorous, this is actually not a function but a distribution. So it's something that's 0 everywhere except that at t equals 0 is infinity. And but still write a 1 here. This 1 has a very funny meaning. It means that this function has area 1. Okay, so it means that it's 0 everywhere except when you do an integral around this thing, you will get the area 1. Okay, and yeah, so that's a unit impulse and a unit step for continuous design case. I guess to get more idea about this, let's see how this is defined as the limit of some function, some more well-behaved function. Okay, so u of t is defined as the limit of those u sub triangle function when triangle goes to 0. And u sub triangle function, look at this. So it goes from it's 0 when t less than 0 and 1 when t bigger than triangle, and it's a linear interpolation between 0 and 1, between 0 and the triangle. And so you think you take a triangle go to 0, then this gets steeper and steeper, and then finally it becomes this function. Okay, and then a weirder function is this delta subtriangle function. So delta of t, once again, is a limit of delta subtriangle function, taking limit when triangle goes to 0. And delta subtriangle function, look at this. It's 0 everywhere except between 0 and the delta is rectangular with area 1. Okay, so it's height 1 over the triangle and has width triangle. So if you think about the area of this thing, is 1. And so you can think about when you take a triangle smaller and smaller, the width of this rectangular area gets thinner and thinner, but the height also goes higher and higher. And at the end, we write it as this thing. So it's arrow here, and the 1 here means the area is 1. Okay, and yeah, so that's the delta of t function. And here we have a few properties here. I guess. So this delta t is a really weird function, and one of the properties here is that delta of t can actually equal to delta of minus t. This is a bit funny because when you look at this function, you see that it's not symmetric. It's not an even function. So delta subtriangle of t is not equal to delta subtriangle of minus t. But when you take a limit of triangle equal to 0, because its width actually goes to 0, so you think delta of t is actually an even function. Delta of t equal to delta of minus t. Okay, and so that's a bit digression, but back to the relation between u of t and the delta of t. And so one very important thing between delta of t and u of t is we would like to get delta of t something from u of t. And we take inspiration for something before we take a limit. So when we think about this delta subtriangle and the u subtriangle, we see that delta subtriangle is actually a derivative of u subtriangle. Because you take a derivative of this function is 0 on those constant part. So 0 when t less than 0, 0 when t greater than triangle. And the slope here is 1 over triangle. Okay? And so we see that the delta subtriangle is the derivative of u subtriangle, and we think this relation should hold when we take triangle equal to 0. And so one of the very important property between unit step function and the delta function is delta function is the derivative of unit step function, because we think this is true, and we take the limit of triangle equal to 0, then delta of t equal to du dt. Okay, and another important property is is that you can get u of t from delta of t. Okay, and actually, so this is similar to the discrete case. So we think we'll place the delta of tau here. So here we have a variable tau. So we place the delta of tau at tau equal to 0, and we do an integration around this thing. So integration from minus infinity to t, and when the integration doesn't touch this spike here, then obviously you are integrating over a whole bunch of 0, then the function should be 0. And but when t is greater than 0, then you are integrating over this delta of tau. And as we said before, this thing has area 1, so when you do integration over it, this should be, when you do integration over it, then it should become 1. Okay, and so those are kind of the two important properties you should remember for continuous time delta function and the unit step function. That is, delta function is the time derivative of the unit step function, and when you integrate through this delta function, you get an area of 1. Okay, and then you can do more change your variable and write your unit step function as a different integration of the delta function. Okay, and now back to the important thing, we want a sampling property. Okay, so sampling property for the continuous time function is a lot like the sampling property of a discrete function, and the result is that x of t times delta of t equal to x of 0 times delta of t. So you multiply the function with the delta function, you will sample all the x equal to 0 part. And then we can do kind of a derivation for this fact by thinking about how this thing, how those equations evolve as the limit with the delta subtriangle. So we think about x times the delta subtriangle, then x of t times the delta of subtriangle, then you will be a function that look at x of t and only between 0 and the triangle. And when the triangle gets smaller and smaller, then assuming your x of t is smooth, then this whole function will look more and more like x of 0, a constant x of 0 function here. And the height here will be 1 over triangle times x of 0, and so when you take a limit of the triangle equal to 0, this becomes x of 0 times delta of t. Okay, and then similarly you can pick out x of t at different points at t0, so you just multiply with delta t minus t0, so x of that will equal to x of t0 times delta of t minus t0. Okay, so that's a sampling property for continuous time. Okay, and finally we see some case that some example that teacher let us get a bit familiar with the property between delta function and the unit step function. That is, we start with this signal x of t with this weird shape. So this is a signal with several steps. So it's 0 when t less than 0, and 2 between t between 1 and 2, and minus 1 between t from 2 to 4, and 1 when t is greater than 4. Okay, and then we can think about the time derivative of this signal, and then it's the signal is a linear combination of several step functions. And so whenever you have a step here, when you take a time derivative, you will get a delta function. So you take a derivative of this signal, you will get a delta function of spike plus, a delta function of height plus 2 here. So here we write a spike. So the height is actually infinite, but the area is plus 2. And then you take a time derivative at this discontinuity here, then you get a spike with height minus 3, and finally, because it goes from 2 to minus 1, and the entire derivative here, you get a spike from spike of height plus 2. Okay. So yeah, so this is the example tells you some relationship between unit state function and delta function. So you have several state function, and you take a time derivative, then you get a several spike at each discontinuity. And I think you can, yeah, and you can check that when you integrate this back, then you get back to this function, because you integrate this 3 spike back, and so you integrate from minus infinity, so it keeps from 0, and you integrate through this spike equals to height 2, and then it keeps us constant between this 1 and 2. Then you integrate through this spike, then it drop minus 3 units, so to minus 1, and then you integrate through this spike, you get this plus 2 back. Okay, so yeah, and then we can have a more algebraic expression for this example. We can say we can write this 3-state function as a linear combination of a 3-state function, 3 unit state function. So it's 2 times the unit state function starting at t equal to 1, and minus 3 over unit state function starting at t equal to 2, and plus 2 over unit state function starting at t equal to minus 4. And you take a time derivative, then you get a 3 delta function, and then you can integrate back to get 3 unit state function. Okay, any question about the unit state function, discrete and the continuous time? Yeah, and I guess, yeah. So those are definition and some property. So unit impulse function is a difference or differentiation of a unit state function, and the unit state function is accumulation or integration of the unit impulse function. And the unit impulse function is nice because it let us sample the signal at a different time step. Okay, and if not, then finally we can go to systems. Okay, and systems, just like signal, they are continuous time and discrete time system. So system with continuous time input and output is a continuous time system. Is a continuous time system, and a system with a discrete time input and output is a discrete time system. Okay, and yeah, just here. So and just as we said before, we have a really funny notation for system, and so we write a system by its input and output pair. So we have some input signal x of t and the output to y of t, and the system is this little arrow here. So system is no name. Every system is written as the same small arrow here. And we basically specify the system by its input and output relationship. Okay, and so system and the system with continuous time input, continuous time output is a continuous time system, and the system with discrete time input, discrete time output is a discrete time system. So and some system example, and I think this we see in introduction. So we can have a RC circuit, and this is RC circuit. So you have some driving voltage, and the resistor here, and the capacitor here, and you solve physics. And you can think about what are the input and output here. So maybe the input is the voltage here, and the output is the charge in a capacitor. And you solve the and you solve the physics. You find out that the input and output can be related to a differential equation. So you see that this output y of t satisfies this equation. So dy dt plus ay of t equal to bx of t, where this a and b here are some physical constant here. So a is 1 over rc, b equal to 1 over rc. This is equal to some physical constant here. And I guess this is a special example that we'll see a lot throughout the course. That is, sometimes the specification of a system is not very direct. I guess, yeah, it's indirect. So if you write down like this, you think you can always calculate y of t from x of t directly. But sometimes you have this kind of implicit relationship, differential equation. You have some relationship between y of t and x of t, and you need to solve this differential equation to see that how the system actually how the system map x of t to y of t. And yeah, so this is solving differential equation, solving system expressed by differential equation is one of the topic of this course, important topic of this course. Okay, and yeah, and then we have more system example. So we now have a discrete time system, and once again we have the implicit equation to describe this system. Anyway, so this system is a balance of a bank account. So the input signal is a deposit you have nth month, and the output signal is a balance of the account on the nth month. And then we assume the account has 1% interest every month. And so then we can see that the amount of money you have in this account is your original money plus 1% interest over previous month plus how much money you deposited this month. Okay, and yeah, so write down this as the equation. So it's y of n equal to 1.01 y of n minus 1 plus x of n. And once again, you have this implicit, now it's called difference equation. And yeah, so you have your system expressed by this difference equation, and would like to know what's actually y of n expressed by x of n, or given x of n, how you calculate what's its y of n. Okay, and then we have more physics example. So with automobile system, so your car, then you can have input as the force and output as the velocity, and then you can digitalize those numbers. So you you take time into some discrete intervals, then you can have the force and the velocity at different time steps, okay, etc. And another concept that it's pretty nice to have, but fortunately we don't have too much time to go into detail, is interconnection of system. Okay, because we want to build a more complicated system, and to do the thing we want to do, to have the input and output relation we want. And easy way to do this is build up from easier components. So we can interconnect different systems together. So for example, we can string two systems like this. So you have input to system 1, and the output of system 1 is feed as the input to system 2, and you get output. And then you can also have the parallel interconnection. So you can have input and copy it to two different feed, and so you copy the input to two string, and one will feed to system 1, another one feed to system 2. And then you add the output together and get the output of system 1 and system 2 together to get the output of the whole system. Okay. And you can imagine you can have more complicated connections, so you can have a hybrid of a serial and parallel interconnection like this. And yeah, so you can split your input to different string and feed to different system series, and add them together and feed to more system, etc. Okay, and this is really straightforward. And really funny thing is we can also consider system with feedback. Okay, and yeah, so now this is a very complicated system because the logic flow is a bit weird. So you can think about you have a system as the input, and so first you feed your input to the system 1, and for the output you split the output to just a straight output and feedback part. Okay, so you feedback the output to go through another system 2 and add to your input. Okay, so system like this is also allowed. So then we can still think about what kind of input will let this system be stable, because it's a very complicated system, and you have this feedback connection. And if you don't design this carefully, then sometimes this thing is very unstable, and your signal will blow up, etc. Okay. Okay. So that's a more complicated system with feedback. And anyway, so those are concept of a system. And what time is it? We are Oh, okay. Yeah, and we have 7 more minutes, right? Okay. And so that's a very high level introduction of system. Any question? Otherwise, let's go to system properties. Okay. So we have basic system properties, and so there are 1, 2, 3, 4, 5, 6 of them. We'll talk about, and yeah. So we'll talk about those properties of systems, so whether a system have each one of those properties. And I guess of those properties, the last two are most important. They are time invariance and the linearity, because from the later part of the course, we'll focus a lot on system with both time invariance and linearity, and those are called LTI systems. Okay. And yeah, let's start with the first system property, that's memory. Okay, and system with or without memory, and so basically this is defined for the system without memory. We have a very strict definition of a system without memory. So a system without memory is a system where the output at some t is only affected by the input at time t. So basically, y of t can be calculated just from x of t. Okay, if a system for all t has this property, for all t and for x of t has this property, then the system is called memoryless. And if the system is not memoryless, then we say it has memory. And this current case is similar, so just change t to n. Okay. And let's see some example of memoryless system. So say y of n equal to y of n equal to x of, is a very complicated function on x of n, 2 times x of n minus x of n squared and a square. And yeah, this indeed is a memoryless function, because you know x of n and you know y of n. Okay. And then you can also have y of t equal to just x of t. This is an identity function, and y of n equal to x of n. And because obviously y of t you can just calculate from x of t. Okay, and then maybe let's see more example that has memory. That's y of n equal to summation k from minus infinity to n x of k. This is an accumulator, so y of n is the summation of x of n, summation of x of n from time to time equal to minus infinity to n. Okay, and obviously this thing has memory because you remember all the previous x of n. Okay, so say y of n will depend on x of n minus 1. And similarly, you have continuous time case, then y of n equal to this integration from minus infinity to t x of tau d tau, then this thing y of t will depend on x of tau, tau not equal to t. Okay. And then maybe either example, we can have a delay signal, y of n equal to x of n minus 1, then obviously this thing depends on x of n minus 1. It doesn't just depend on x of n, and we can also have an advanced signal, so y of n equal to x of n plus 1. Okay, those are examples. And I guess let's have a quick question, extra question here. So what about this function? Oh, excuse me. Where am I? Here. Sorry. Oh, here. Why did I see? This is very annoying. It is bugging out. Oh, okay. Now I'm big. And yeah. So let's say I cannot get it. Okay. Then so y of n equal to n times x of n. So okay, need to draw with my mouse. Okay, so what do people think about y of n equal to n times x of n? Do you think this is memoryless? Then raise your hand. And this thing has a memory, then raise your hand. Yeah. And I think this thing indeed is still memoryless because although we are a little imprecise here, so y of t, y of n only depends on x of n, and so basically you know x of n and n, then you can calculate y of n. Okay. And indeed, although this is depend on n, it doesn't depend on all other x of n. So it doesn't depend on x of n minus 1, x of n minus 2, or x of n plus 1, x of n plus 2, etc. So here, you can calculate from n and x of n, then this thing is memoryless. Okay. And I think it's next time to take a break now. And next class, we'll finish other properties of the system. Okay. Yeah, let's take a 10-minute break, and let me try to fix this. Why does this thing?为什么不能用？这样。黄子浩的就是助教费那部分的话，没有想到怎么处理。就是你领了，然后你给他钱。对，就是我，就是因为好像今天昨天你有寄给我，那个什么英文哦，那个英文的。英文的部分，因为我看你好像没有寄到他。哦，我想说就给你处理的。那个他可以吗？我不太确定。可以问问看，但是那个是我要去弄的吗？还是没弄就没有？我猜是没弄就没有吧。OK， 好，那我回去之后去研究一下。OK。这个怎么这么难用？为什么如此难用？
谢谢。
get back to our second class. Okay, gets back. And yeah, we will finish talking about the other 5 properties of the system, and maybe we can even be break a little earlier. Let's see. Okay, and yeah, so the next property of systems is invertibility, and related to it is the concept of inverse system. And I think the concept is pretty straightforward. So a system is invertible if there is another system that can turn the output of your system to the input of your system, and obviously for all input. Okay, and you read this as a block diagram. You look at this. So your system has an input and output, and there is this inverse system that can always have its output just equal to the input here. And then we have an example of a very easy invertible system, that is y of t is 2 times x of t. So your output is just twice your input. Then the obvious inverse system is just divided 2 back. So you can have another system where the output is 1/2 of the input. So we return it in this way. So wt equal to 1/2 y of t. And yeah, and then you string those two systems together, then you see that w of t equal to x of t. Okay? And then this trivial system that's invertible, this is a summation system. So x of n, if go to this system of accumulation, so y of n equal to summation k from minus n to infinity, k from minus n to minus infinity to n s of k. So y of n is the accumulation of x of n from minus infinity to now. And then you can actually calculate the x of n from y of n if you know all of y of n. So you can have x of n being a difference function, difference system. So the second system is the w of n equal to y of n minus y of n minus 1. And you can easily check that you take the difference of the accumulation, then it's actually just the input. So w of n is x of n. This is a bit related to the difference of state function equal to the unit impulse. But anyway, the accumulation function has inverse. Okay, and then we can think about, we have an example of where the system is not invertible. So for example, y of t equal to x of t squared. Then this is not invertible because basically because you lose information. Okay, so you think about, you have some x of t and some minus of x of t that will give you the same y of t. And because there are two different inputs have the same output, so obviously, so this is not invertible because you don't know whether you want to invert your y of t to x of t or minus x of t. Okay, and yeah, so here we have a bit of a strategy for doing this kind of problem. So in your homework exam, you will be asked whether to determine whether the system is invertible or not. And if you want a rigorous proof, so when it's invertible, then you need to find the inverse system. And when it's not invertible, then you want to find a counterexample where two different inputs give you the same output. Okay. And so that's invertible. And the next one is causality. This is a very physically intuitive idea. So causality means that the current value of your output only depends on input, the value of input from now and the previous time. Okay. And so this is a weaker property than memoryless. Memoryless says that the output at this time step only depends on input at this time step. And causality says that the output of this time step only depends on what the previous input it has. Okay. And the other way to say this is that the input at this time step is independent of input at the future. Okay. So y of t, so for continuous time, y of t is independent of x of t plus tau for all the tau greater than 0. And for discrete time, y of n is independent of x of n plus k for k greater than 0. So the output at this time step doesn't depend on input at the future. And you can think, you can feel that all the most of the physically motivated systems should have causality, because what happened right now should not depend on the future, should depend on what happened in the past. Okay, so here we have two very physical examples. So we have this RC circuit example and your car example, and the charge on your capacitor should only depend on voltage in previous time, and the velocity of your car should only depend on the force of all the paste on this car. Okay, and so all the physical systems are causal, but we can also build non-causal systems. So say mathematically we can just define some non-causal system. So maybe your y of n is just x of n minus x of n plus 1. Then obviously this y of n will depend on x of n plus 1. And say even more straightforwardly, you can have your y of t just equal to x of t plus 1. So this is, I think this is called advanced signal. Okay. And then you can also have this kind of averaging function that will also be non-causal. So your y of n will be the average of your x of n between k equal to between just n and plus minus m. So this is y of n is some smooth out the signal of your x of n, and this is something maybe you will do in your I don't know, in your image processing. Maybe you want to make your imaging smoother, then you can calculate this function on your image, etc. This kind of smooth out function. And anyway, so you can also have a non-causal system where y of n depend on the future x of n, or y of t depend on future x of t. And yeah, so now two examples. And I guess it's now to do this yes/no question. So is y of n equal to x of minus n causal or not causal? If you think it's causal, raise your hand. If you think it's not causal, raise your hand. Anyone? No one want to answer. Or maybe think a little more. People think for 10 seconds. Is this causal or not causal? Y of n equal to x of minus n. Okay, so let's do this again. Is this causal? Raise your hand. If this is not causal, raise your hand. Okay, yeah, and indeed this is not causal, because you need to think about all possible n. Okay, so it's easy to think this is causal, because for n greater than 0, it only depends on negative n. But you think about n less than 0, then this negative n will depend on positive n. And that's non-causal. So in particular, y of minus 1 depends on y of plus x of plus 1. Sorry. Okay, and yeah, so we have a big example. So here the example is minus 4. So y of minus 4 depends on x of 4, and 4 is greater than minus 4. So this is not causal. Okay, and sorry. Okay, and second question, y of t equal to x of t times the cosine t plus 1. Is this causal or not causal? And let everyone think a little bit. And they think it's causal, raise your hand. Okay, and they think it's not causal, raise your hand. Okay, and yeah, most people get it correct. And so this thing has a tricky part, cosine of t plus 1. But the cosine of t plus 1 doesn't depend on x of t. Okay, and for causality, we only care about the relationship between x of t and y of t. Okay, and so how y of t depends on x of t is just y of t so this thing is actually memoryless. So y of t only depends on x of t, and times another part that just a function of t. So this is cosine t plus 1 thing. Although you have t plus 1, looks like something in the future, but this doesn't depend on x of t overall. This is just function of t, and you can calculate function of t. Okay, and yeah, so indeed this is memoryless and causal. Okay, and cosine of t plus 1 is just a function of t. Okay, and let's go to next property. That's stability. Okay. So here we have a sketch that gives you an intuition of stability. So we want to study whether a system is stable or not. And we think about those two examples. So you see you have a pendulum that hands down right here, and you think this system is kind of stable because you push it a little bit, and it will just oscillate around this area. Whereas if you put a pendulum, this stick up, and you push it a little bit, then it will fall down and it feels unstable. Okay, and so this is the intuition of stability. It actually doesn't totally fit the definition of stability we are going to give. Okay, and the definition of stability we are going to take in this course is this bounded input and bounded output stable. Okay. And this means that the system is stable if for bounded input you get a bounded output. So I guess we have two drawings that give a bit of idea of unstable and stable function. So you think about your input is x of t and the output is y of t. So x of t is blue line, y of t is origin line. And stability means stable means kind of feel like you have this bounded input and somehow your output just diverges to infinity. So this is unstable. And whereas if you have this bounded input and your output just oscillating in some bounded range, then this is stable. Okay. So this is a bit of a confusing concept because you need to remember that this concept is really this stability, this is really a property on system. Okay, so this is a property on system, a property on your input signal or output signal. I guess it depends on output signal, but really this is a property that depends on the relationship between input signal and the output signal. Okay, and once again, the definition is that you have a bounded input, then you have a bounded output, and bounded input means that the absolute value of the absolute value of your signal is bounded for all t. So it means that it's all bounded between some plus value and some minus value. And so then you have this bounded input and then you have a bounded output, then this is stable. Okay, so example of stable system is y of n equal to x squared of n. Okay, so you see if your x of n is between some value, say some is less than some b, then then your y of n obviously is less than b squared, so this is bounded. Okay, and an example that's not stable is our bank account example. So y of n equal to 1.01 y of n plus x of n. So this is not stable because you think you store some finite amount of value at some time, so your input is bounded. But then your output, because of this interest part, will get exponential growth. So even if the amount of deposit is finite throughout time, the total balance of your account will go to infinity as n go to infinity. So this is not bounded output. Okay, and so now we can have more example. So System 1, System 2 is BIBO stable, is BIBO stable. Okay, so System 1 will have t equal to t times x of t. Okay, then people think a little bit how this system should evolve. So you have a bounded x of t is y of t bounded. Okay, if you think this is stable, raise your hand. If you think this is not stable, raise your hand. Okay, so this is a tricky example, and this is actually not stable because there exists a bounded input where y of t is not bounded, and the bounded input is very easy. It's just x of t equal to 1. So obviously x of t equal to 1, the whole function is bounded between 1 and minus 1. So this has a bounded value. But y of t equals to t times x of t, and this is unbounded because as t goes to infinity, this is equal to infinity. So you have a bounded input giving unbounded output. So yeah, so this is unstable. Okay, and then the second system is y of t equal to exponential x of t, exponential of x of t. And do you think this is bounded input, bounded output, stable or not? Okay, so if you think this is stable, raise your hand. Okay, and if you think this is unstable, raise your hand. Yeah, then yeah, people are getting better at this. Okay, and indeed it is stable because once again you think x of t is bounded by some number b. Okay, so our value of x is less than b. Then you can see that your y of t, although you have an exponential part, this is really large, but it's bounded by some finite value. So b is some finite value, and e to the b is still some finite value. So if x of t is bounded by b, then you can easily calculate that y of t is bounded by e to the b. Okay. And yeah, so indeed it is stable because for every bounded x, you have a bounded y. Okay. And yeah, so here we have some drawing that kind of drawing that kind of show the example of two functions here. So here is y of t equal to e to the x of t. So you have bounded x of t, then your y of t will get a much larger oscillation, but it still have a bounded oscillation. Okay, and whereas your y of n is just accumulation. Okay, so this is a different example than we have. But if y of n is accumulation, then you have a bounded x of n. So say x of n is this unit state function. This is bounded between y and -1, and then this is an unstable system because y of n will keep adding more and more, and you go to infinity, there is no bound on your y of n. Okay, so this is BIBO stable, and yeah, sometimes it is very unintuitive, but you need to remember the definition, so you test whether all bounded input give you bounded output. Okay, and so that's stability. And the next one, I think it's I don't know, it's very important, but it's a bit less intuitive. So it's time invariance. Okay, and but it still has a very strong physical intuition. That is, you think about a physical system where its behavior is fixed over time. Okay, so say you have this RC circuit here, and you think if your resistance here and the capacitance here doesn't change with time, then your system kind of its behavior doesn't change with time. Although you can have a different input signal and a different output signal, and but the relationship between, so your input signal can depend on time, output signal can depend on time, but you think the relationship between input signal and output signal should not change with time because the R and the C here are same throughout all the time. Just remember let's see if we can remember the differential equation we write out for that system. So you think this differential equation doesn't change with time. So there is something about x and t, something about the relationship between x and y doesn't change with time. Okay. And similarly for your car, if your car don't get all two-faced, and your car doesn't change too much throughout time, I guess your car doesn't change throughout time, then the response always between its velocity. Oh, sorry. This is about causality. So let's go back to time invariance here. Yeah, so if the car doesn't change throughout time, then the response always velocity and the force also doesn't change through time. Okay, and so that's a nice idea, but when we want to write down this mathematics, then it's quite complicated. I guess it's a bit complicated. So how do you describe this system doesn't change with time? Is you think about you shift your signal. Okay, so you use this time shift property to test whether I guess not time shift property. You use time shift transformation on your signal to test whether your system doesn't change with time. And so what we do is we say for input output pair, so you have some input, you get some output, and you think if your system doesn't change with time, then if you just start this system with later time, so you shift later or earlier time, so you shift your input by some time n naught, then the response, your output should just be the same output shifted with the same time. Okay. Because you think the input output pair, the relationship between input and output should not change with throughout time. So if you shift your input by some time step, your output should just be the same output shifted by the same time step. And similarly for continuous sign case, you shift by t naught for the input, then you will get the output shifted by t naught. Okay, and I guess let's see some example. And here the example we already have an answer here. This one let's just go straight through. So x of 1 go to x. So y of t equal to sine x of t. So this is a quite complicated function. So y of t. But anyway, this you see this is a memory-less function. So y of t is just a sine of x of t. And anyway, so x of t. So you get some x1 of t, and then you get some y1 of t. So you have this input-output pair. So for arbitrary x1 of t. So y1 of t, as specified by this equation, should be sine of x1 of t. And then how we check whether the system is time invariant is we kind of go through this square. So we shift the input by some t naught, as we say we want to do. So we get x2 of t equal to x1 of t minus t naught. And then we want to check two things are the same. So first is you have this x2 of t as input and get the output. So you have y2 of t equal to excuse me. So you have y2 of t equal to output from x2 of t. So sine of x2 of t, so that's the sine of x1 minus t, x1 of t minus t0. And they want to check this y2 of t is the same as the other function. That's is y of t minus t0, right? So we want to see this y2 of t is y1 of t minus t0. Okay, and indeed that check out. So you take this y1 of t and change t to t minus t0, then you see that this is the same as y2 of t. And so in general, this is what you want to check. So you put arbitrary input x1 of t through your system, you get y1 of t. Then you shift your system by strip the input x1 to x1 of t minus t0, and then you do two calculations. One of them is you put this thing through system again, then you get some y2 of t, and then you shift this y1 of t by time step t0, so you get y1 of t minus t0, and then you want to have y1 of t minus t0 equal to y2 of t. If they are the same, then your system is time invariant. If they are not the same, then your system is not time invariant. Okay, and here, okay, so we have already some answer here, but I guess we can still do a quick verification. So quick voting. And so is the system time invariant? So y of n equal to n x of n. And you think this is time invariant, then raise your hand. And if you think this is not time invariant, raise your hand. Okay, yeah, and indeed this is not time invariant. I guess very intuitively, you have n part here that just depend on time. So at every time step, the response of your y is just the input, but times is n here, which totally depend on time. So you can feel that your system characteristic totally depend on time. And we can have a very specific concrete example here. So say your input is delta of n, then the output will be 0 because delta of n is non-zero only when n equal to 0, and n equal to 0, then you have 0 times n, delta of n equal to 0. And if your input is delta of n minus 1, then it's a spike at t equal to 1. Then your output is 1 times delta of n minus 1, then this is non-zero. Okay, and so this is non-zero, and this is not a time shift of the zero function. Okay, and more example, and I guess we can see this more example here, and I guess we can see a picture, and if we want to calculate the equation is here. So y of t equal to x of 2t. Okay, and we see that okay, and existing time invariant is I guess it's a little harder to judge from just writing here, and but once again we can do this block to check, or we can do an example to check. So say if our x over t is block wave function, so from minus 2 to 2 is 1, then its corresponding output y1 of t will be because you have times 2 on t here, so it will be compressed. So it's 1 between -1 and 1. Okay, and now we can have a time shift of this thing. So your x of t got transferred by step 2 to the right. So your x of t, 2 of t is x1 of t minus 2, and it's a backward between this. And then the y2 of t will be once again shrink to the 0 line, so it's a wave between 0 and 2. But then you compare this to y1 of t minus 2. So if you have y1 shrink by 2 blocks, then you see you have a block between 1 and 3, and that's different from this block between 0 and 2. So you see this system is actually not time invariant. Okay? Because it's compressing to the middle, and so I guess on a high level, because this system is compressing your signal to the t equals 0, so that makes t equals 0 spatial throughout this t line, and this is not time invariant. Okay, so that's time invariant. And any question? Yeah. And here is the calculation you do on this thing. So you have some x1 of t, then you calculate y1 of t, and then you have x of t, 2 of t equal to tangent of x1 of t. Then you can calculate 1 of t minus t0 equal this thing, and the y2 of t equal to x2 of 2t. And you see this equation and this equation is different because it has 2t0 here and this is only t0 here. Okay. And finally we go to the next property, linearity. Okay, so linearity is I guess the most important property of the course, because we'll spend a lot of time talking about linear system, even when I guess most of the time I talk about LTI system, but the linearity I feel is personally I feel it's even more important than time invariant. But anyway, so what's a linear system? A linear system is a system where the response is linear. So it means that the output is linear input. So basically this equation, those two equations. So when you think about, you have two input and output pair. So you have some input x1 giving output y1, and some input x2 giving output y2. Then if you input with a linear combination of x1 and x2, you get a linear combination of y1 and y2. And in particular, you can write it. So there are two ways to write this. So first is you write down those two equations. So if you have addition of x1 and x2 as input, then you have addition of y1 and y2 as output. So that's additivity. And another is you have scaling. So if you scale x1 by some number a, then you get y1 scaled by the same number a as output. Okay. So this is called scaling or homogeneity. Okay. So we have additivity. If a system satisfies both additivity and homogeneity, then this is a linear system. Okay. And here we take a scalar to be any complex number. Okay. And so this is a linear system, and the continuous case, this is very similar, so that's not right out again. You just change bracket n to parentheses t. Okay, and but one nice consequence of linearity that you should kind of remember is that actually just from the homogeneity is that if your system has homogeneity, then you have 0 as your input. So if your input function is constant 0, then the output it will be also constant 0. Okay, so homogeneity implies that constant 0 goes to constant 0, because you can write a constant 0 function as the 0 scalar times the arbitrary function, and then by homogeneity, then a equals 0 here, you should map to 0 times the whatever output function, but this whatever output function times 0 will still be 0. Okay. So by homogeneity, 0 function will always get mapped to 0 function. Okay, that's one consequence of homogeneity. And then just as I say, so this is one way to write the system being linear. You need to satisfy additivity and scaling. And but you can also write this as either way. It's very easy to see this condition is same as the previous condition, so let's not do a proof. Another way to write this is you can think about superposition property. So your signal is a linear combination of some input signals, so a summation over some index k, and you have different coefficient ak for each sk, and you have this linear combination between different sk. So if your input is this linear combination of different sk with coefficient ak, then output will be the same linear combination. So the output will be linear combination between yk with the same coefficient ak, where we say that we assume that each sk has yk as input, as output. Each sk input has yk as output. Okay, so you have a linear combination of input, then you will get the linear combination of output with the same linear coefficients. Okay, so yeah, so this is another way to write the linear system property, and it's called the superposition property because we think x of n is writing x of n as a linear combination of xk, as this is a superposition of different xk. Okay, so linear system is really nice because then then you can write your system as a linear combination. Sorry, you can write your input as a linear combination of different xk, and you just need to study how some specific xk make to yk. Okay, and yeah, so for this is for discrete time system, and yeah, continuous time system is the same. You just change bracket n to parenthesis t. Okay, linear combination. Okay, and then let's have some examples. So is system linear? Okay. Y of t equal to t x of t. Okay, and I guess the answer is here, so it's a bit dumb to ask you whether this is linear, but you can think a little bit, and yeah, we can check whether this system is linear or not by doing calculation. Okay. I guess from the equation just here, it's not very obvious, so it's better to do a check yourself. Okay. And anyway, so what we want to check? We want to check once again is a square here, so we put some x1 to y1 pair, x2 to y2 pair. Then we want to check a linear combination of x1 and x2, so ax1 plus bx2 give maybe to some y3 that equal to the linear combination between y1 and y2, so ay1 plus by2. Okay, so this is what we'll do, and so we have some x1 of t, and then we'll map to y1 of t equal to t times x1 of t. This is by this equation. And similarly, y2 of t equal to t times x2 of t. And then we have ax1 plus bx2, and we call this way x3. Anyway, so this thing maps to some y3. And so y3 should be t times this function, so t times ax1 plus bx2, t times ax1 of t plus bx2 of t, and then now we just have a linearity on this multiplication with t, so this is equal to at x1 of t plus bt x2 of t, and this is a times so tx1 of t equal to y1 and tx2 of t equal to y2. So we see this is ay2 1 of t plus by2 of t. So indeed we have y3 equal to ay1 plus by2 for x1 and x2, and for a and b. So let's check that this system is linear. Okay, so that's how you check a system is linear or not. Okay, and now we have quite a bit of time, so we can do this slower. Okay, so now we have two questions: is this system two system linear or not? Example, I guess it's okay. So let's do this question first. So is this y of t equal to x of t squared? Is this linear or not? Okay, if you think this is linear, raise your hand. And if you think this is not linear, raise your hand. Okay, so indeed this is not linear, as this kind of suggests, because if a square here is not linear, and the counterexample is easy. So you don't even need x of t because x2, because this thing doesn't satisfy the scaling property. So you change x of t to ax of t, then you see your output y is a squared of y. And for general a not equal to a squared, and so this thing doesn't satisfy scaling, so this is not linear. Okay, and now the next question is harder. So is y of n equal to the real part of x of n? Is this linear or not? Okay, so this is a tricky question. So if you think this is a linear, raise your hand. If you think this is not linear, raise your hand. Okay, and as we said, this is a very tricky question because this is actually not linear. Okay, so this satisfies additivity because you have the real part. So you have some x1 plus x2, and you take a real part. That will be a real part of x1 plus the real part of x2. Okay, but the tricky part is remember we said that we take the scaling coefficient can be any complex number. Okay, so we want the real part of ax1 equal to a times the real part of x1. And this is not true if your a is a complex imaginary number. Okay, so say you have a real x and your a is just a complex value j here. Then you change from a real function x to a purely imaginary function x. And this purely imaginary function x taking the real part will become 0. That doesn't equal to j times your real part of x. Okay, so this is quite a tricky question, and this is actually not linear because if you scale by imaginary number, then your system, your output doesn't get scaled by the same imaginary number. Okay, and the next question is this system looks very linear. I guess the answer is here, but so let's not ask you. And this is another tricky question where the system looks very linear. So y of n is a linear function of x of n. Okay, so y of n is 2 times x of n plus 3. Okay, y of n is a linear function of xn, but actually the system is not linear. Okay. And a very easy way to check this is that I guess you can check the homogeneity again. Okay, so you think x1 of n equal to 0, then y1 of n actually equal to 3. Okay, but remember we say that if you satisfy homogeneity, then 0 should always map to 0. Okay, so just from this 0 map to 3 example, you already see this is doesn't satisfy homogeneity. It's not linear, and you can check it even more. So it also doesn't satisfy additivity because you have another x of t. I guess this is basically the same example, but you can have x1 equal to 0 and map to 3, and x2 equal to 0 map to y2 equal to constant 3, and x3 equal to x1 plus x2 is still 0, and then y3 will equal to 3. It doesn't equal to 3 plus 3. Okay, and so this system looks very linear, but because this plus 3 constant here, it's not linear. And you can do more generic checking we had before, so you can have x1 mapped to y1, x2 mapped to y2, and then you have your x3 equal to ax1 plus bx2, and you see that this y3 is not equal to ay1 plus by2 because the constant term gets messed up. Your constant term will be 3 times y minus a minus b. Okay, and yeah, so this example, if you just want to think about whether it's linearity, whether it's linear, it's not linear, and I guess you want to solve it a little bit about this example is you can say it's kind of linear, and we can introduce a property that we call incremental linear, and it basically means that the system is linear plus some constant part. Okay, and I guess the definition of incremental linear is this. Okay, so definition of an incremental linear system is that the system's output is the input going through a linear system plus something that doesn't depend on input, some constant function, some not constant function, some fixed function y0 of t. So this y0 of t is called zero input response. Okay, and so in our example, y of t equal to 2x of t plus 3. Then the linear part is x of t mapped to 2x of t, and you add zero input response as 3 here. Okay, and but let's say you can have different incremental linear system that actually doesn't look so linear. Is maybe you can have this is hard. Okay, let's try. It's very annoying. So say you can also have y0 of t equal to t, then it's still incremental linear. So as long as your y0 of t doesn't depend on x of t, then this is an incremental linear system. And anyway, the incremental linear system, we don't use too much of it. I think you probably only see it in some part of homework, but it's nice to know it exists. And it has this property that if a system is incremental linear, then the difference between output will be linear in the difference between input. Okay, so your x1 of t go to some y1 of t, x2 of t go to some x1 of n go to some y1 of n, and x2 of n go to some y2 of n. Then your difference between y1 and y2 will be 2 times the difference between, you see here is 2 times the difference between x1 and x2. And yeah, it's linear. So the very high level idea is that you have some x1 goes through this, x2 goes through this, and when you take a difference, then the y0 part will cancel out, then you are just having a linear system. Okay. And yeah, so that's all I want to talk about linearity. And okay, that's very nice. We are on schedule. And here is a summary of first chapter 1. So we go through basic concept of continuous time and discrete time signal. And I guess one thing to say is the discrete time signal is very special in that we take a discrete time step over the integer values. So only at the integer value. And we have a teacher about transformation on the independent variables. So we have the time shift, time reversal, and time stretching. Time scaling. And time scaling we only define on continuous time system for continuous time signal for now. And then we have a periodicity. It's some property related to time shift. If a system is invariant under some time shift, then it has a periodicity. And we have even odd, they are related to time inverse. So if your system doesn't change with the time inversion, then it's even, and you get a minus sign on time inversion, it's odd. Okay, and then we talk about complex exponential and sinusoidal signals. And in particular, we care a lot about complex exponentials of the form e to the j, so where the exponent is purely imaginary. And okay, so this is hard. Okay. So we care about e to the j omega 0 t or e to the j omega 0 n. Okay, and we talk a lot about those two signals because they are the periodic ones. Okay, so if on complex exponential to periodic, they are probably in these two forms, and obviously you can have other coefficients in front. But the most important part is e to the j omega t and e to the j omega n, or e to the j omega n for continuous time and discrete time. Okay, and we see that for discrete time case, the periodic behavior is very different from the continuous time case. So for continuous time case, this omega 0 is totally the frequency of the signal. Omega 0 is higher than the signal is oscillating faster. But for discrete time case, this omega 0, when it gets too large, then this n doesn't see how fast the signal is oscillating. So omega 0 is actually only have meaning between some finite interval between 0 and 2 pi. And also for omega, and also the periodicity of this function is weird. So for omega 0 not rational multiple of 2 pi, this is not periodic. And for omega 0 being rational to 2 pi, if omega 0 is some n over n, then the fundamental frequency will be big N. And omega 0 fundamental period will be the smallest big N you can find. So I guess let's write down that here again, instead of just talking on the fly. Okay, pen. So we have omega, so the thing we just taught today. And where am I? Oh, this is hard because I don't see my pen. Is my pen on there? Anyway, so omega 0 we think equal to 2 pi and n over big N, and we want to find if it's a rational number, it can be written this way, and the smallest possible positive big N here, it will be the fundamental period, and the fundamental frequency will be 2 pi divided by big N, and so that's actually omega 0 divided by m. So when m not equal to 1, then omega 0 will not be the fundamental frequency. Okay, and so yeah, because your signal should need to actually oscillate in a whole bunch of time to get to one period. Okay, so that's periodicity, and then we talk about harmonic related complex exponentials. So those are the functions that have those are the complex exponential functions that all have the same period. And the intuition is, let me see where is it. Okay, the intuition is that you have some fixed period, and it's easier to draw continuous time. You have some fixed period here, and it's really hard to draw without seeing my cursor here. Yeah, and you have some fixed period here, and cannot draw. And then you can have this kind of signal, and then you can have faster oscillation, maybe 2 period in the same fixed big period t, etc. So you can have a signal that has faster and faster oscillation in the same fixed period, and those signals are called harmonic related complex exponentials. And for discrete time case, then so for continuous time case, then you can fit more and more oscillation inside this same period. But for discrete time case, if the length here is n, then you can only fit n different discrete complex exponential here. Okay, and then so today we also talk about unit impulse and the state function, and the unit impulse are the delta functions. So unit impulse delta of t or delta of n, that's right, delta of n, and the unit state function u of t or u of n. Okay, and the impulse spike somewhere, they will pick out value n somewhere, and yeah, oh sorry, yeah, okay, I guess that's just a flip back. So this is 32, and let's try flip back, and so unit impulse and unit impulse and the unit state function look like this. For discrete case it's easier, and for continuous time case, the unit impulse function is infinite spike at t equals 0, and the spike is area 1. And the unit state function is the function that's 0 when t less than 0, and 1 when t greater or equal to 1. And what we really want is that the delta function can sample any function at any point. So x of t times delta of t equal to x of 0 times delta of t. And x of t times delta of t minus t0 will equal to x of t0 times delta of t minus t0. Okay. And yeah, and we also talk about block diagrams, and then we talk about those. Oh, guess we are missing memories. Okay, we have talked about the system properties. So we have memoryless and causality. Causality means the system output don't depend on future input, and the stability means the bounded input, bounded output, and the invertibility means that you can find the inverse function. And time invariance means that you shift the input, you have corresponding shift in the output. Time shift in input, you have corresponding time shift in output. And then finally, linearity, you have additivity and homogeneity. And means that you have a linear combination of input, you should get the same linear combination of output. Okay, and that's all for chapter 1. And see you on Thursday, and we'll start our chapter 2, talk about LTI system. Okay, let's stop here. Okay.